This video is the last installment in a series that introduces Julia programming language and its application towards linear regression models. We have thus far covered the topics of simple and multiple regression in Julia. Next, we will look towards programming diagnostic tests to assess our model residuals. We will also learn how to import code from R programming language into Julia and use R to clean our dataset of outliers. In this video, we are going to be jumping right into Julia to teach these techniques with code. We will be applying diagnostic tests towards the same dataset and models we previously used in videos 2 and 3. To recap, our dataset comprises of over 9,000 observations of measurements at a power plant. We have 4 possible explanatory x's to predict our scalar energy output. We can import code from the statistical language R using the package rcall. To download rcall, we will build it using the build tool in Julia. Next, we can use it with the using function followed by rcall. To import a package from R into Julia, along with its functions it comprises, we will use the @rlibrary command followed by the package name from R. In this case, we will be using the R package mass. When we want to use an R code in Julia, we will write it in the following format: capital R, followed by quotations with the R code inside. We can exemplify this by importing the package mass with the library function using this format. Next, in order to grab our dataset already loaded into Julia and utilize it within our R code, we will use the command @rput, which places our desired object into the scope of R. By typing @rput df, we are telling R to grab df from Julia and allow its incorporation into R code. Now, let's try using the lm function within R to display our full linear model, utilizing all variables from our dataset. If we name this model lm1, we can use it again in later R code, rather than having to use @rput. Next, let's start our diagnostic testing using R. We use diagnostic tests in statistics to measure different forms of accuracy. Here, we are looking to see how well our dataset is constructed by assessing the possibility of outliers in our observations. Outliers are observations that are distant from other observations. Outliers typically arise due to variability in measurements or by experimental error. We exclude outliers to minimize errors and to achieve a more accurate representation of our data, and thus more precise estimations and conclusions. We can code for the residuals of our model using the studRes function from R's mass package previously imported. Again, typing this using R allows us to call upon this later on instead of grabbing it out of Julia. Now we can use @rget to copy the name of our residuals from R onto Julia. Using plots in Julia, we can use the histogram function to display a histogram of our residuals. Here we see a good representation of a normally distributed set of residuals centered around a mean of 0. There is possible indication of outliers, with some data showing up way off our left tail, but overall we see a normally distributed set of residuals. We want our residuals normally distributed because they are needed to follow a normal distribution for the tests of significance to work. Previously in videos 2 and 3, when we used t-tests, we were assuming that our errors followed a normal distribution for the tests to work. Here we see that our assumptions were correct, and we can continue forward with more testing. A Cook's distance plot of our model checks the Cook's distance for each observation, or row from our dataset. Distances greater than 1, or those that are significantly larger than the other distances observed, indicate an outlier in our data. Here the plot indicates a few outliers based on their larger Cook's distance. The row number of these outliers is displayed. A QQ plot is another way to test the normal distribution assumption of our residuals. The data points our plot displays should follow a linear line. We see this to be very true during most of our line, although the ends of our linear line show some discrepancies in the data. Each tail seems to move farther away from our line, and a few row numbers displayed indicate possible outliers in our data. Some of these are the same observed in our Cook's distance plot. Now let's further this testing using an influence plot. We use the R package car in order to import the function influence plot from R. An influence plot checks for data points that may have an undue influence over the regression line. Again, we see some similar row numbers indicating possible outliers. This influence plot seems to generate the most outliers. Our next steps would be remove these rows that our residual testings indicated are outliers in our data. We could then continue our linear regression with more precise estimations that more accurately depict the majority of our data points that follow similar trends and are not dependent on experimental errors. Another way to remove outliers in our data is to look for outliers in the residuals of each variable of our dataset. Let's try this with the variable vacuum. We will use R to fit a basic linear model with vacuum, predicting energy output. Next, we use R again to find the studentized residuals using the studRes function from the mass package. Let's name them resids1, as to not confuse them with our previously calculated residuals. We will be using Julia to omit our residuals of outliers, so we use @rget to bring resids1 into Julia. The following for loop checks for residuals distance and standard deviations. This loop creates a variable, outlier array1, which produces a 1 when a residual is 2 standard deviations away from 0. 2 SDs was arbitrarily chosen, and users can change this based on their personal preference and preferred precision levels. When a residual is less than 2 SDs away from 0, outlier array1 produces a 0. Note, our residuals are squared here, and so are our 2 standard deviations, which is why we type a 4 here. Please be wary of this when choosing your measurement. We can next create a new column in our data frame df using the following format to create a vector of our outlier array with 1s and 0s. Let's plot our vacuum variable against energy output. We use the new outlier column in our data frame to color our possible outliers orange and the rest of our data points blue using the following format. We can see that this for loop worked well in locating our outliers in the data. Now, let's modify our data frame by only including rows which have an outlier value of 0, meaning we are omitting the captured outliers from our data. We now plot our new data frame and see that it is rid of outliers and now displays a better linear relationship than before. Let's now run the lm function to compare our original basic linear model with our new one to see how omitting the outliers affected our model and estimated coefficients. There's not much change, although we do see a minimization in our error term, and we can assume our new model coefficients do a better job at representing the general linear trend in our data than the original model had. This was exemplified in our plots. Now, let's move on to one last topic, transforming data. We can scale data through different transformations, which can, in turn, display our dataset with a more precise distribution, or just simply transform variables onto a common scale. Sometimes, our data can comprise of many different measurements with numerical differences that are significantly large. Scaling our data can make them easier to work with and can potentially minimize variance and error. Let's take the linear model of our full dataset. We can view the estimated intercept and beta coefficients of each term. Now, using the following for loop, we can center our x values around their respective means. In doing so, we will not change our beta 1 through beta 4 estimates, but rather slightly change our beta 0, the intercept of our model. Originally, the intercept did not mean much, other than the value of y when each x was 0. This was never necessarily the case. Now, after mean centering our x's, the intercept is the mean of our y when each xi is equal to its mean value. This transformation of mean centering our data allowed for an intercept value that could be interpreted better, without changing our other beta estimates. If this were our preferred method of modeling our data, we could continue further with our linear modeling and graphing. Other forms of data transformations could allow us to interpret our data in other forms, based on our personal preference or initial experimental approach and goals. This concludes part 4.4 in our series. We have introduced the basics of the programming language Julia and its application towards the topic of linear regression. Julia is a great tool for scientific and numerical computing and features good, efficient performance with clean output. Juno IDE features a high-quality environment for statistical computing, rivaling RStudio and other integrated environments. We hope you enjoyed this series and the Julia language. Thanks for watching.